Hello everyone, welcome to the channel Amazing Civil Engineering Studies.
Hello friends, in this video we will study about concrete formwork. Concrete formwork. Definition. Formworks for in situ concrete work is defined as a mold or box into which wet concrete can be poured and compacted so that it will flow and finally set to the inner profile of the box or mold. Formwork can be made using molds out of steel, wood, aluminum, and/or prefabricated forms. Formwork is an ancillary construction, used as a mold for a structure. Into this mold, fresh concrete is placed only to harden subsequently. The construction of formwork takes time and involves expenditure up to 20 to 25% of the cost of the structure or even more. These are temporary structure required to safely support concrete until it reaches adequate strength. Functions. Forms mold the concrete to desired size and shape and control its position and alignment. Formworks also act as a temporary structure that support its own weight and the freshly placed concrete and construction live loads, material, human, logistic. Formwork is a classic temporary structure in a sense that it can be erected quickly and it is highly loaded for a few hours during the concrete placement. Within a few days it is disassembled for future use like any other temporary structure. A good shuttering would have the following characteristics, that is, safe and cost-effective or economical. High quality, finished concrete surface is of acceptable quality in the correct location, able to produce the required shape and surface. Strong enough to withstand all types of dead and live loads, rigidly constructed and efficiently propped and braced both horizontally and vertically, so as to retain its shape. The joints in the formwork should be tight against leakage of cement grout. Construction of formwork should permit removal of various parts in desired sequences without damage to the concrete. Material of the formwork should be cheap, easily available, and should be suitable for reuse. The formwork should be set accurately to the desired line and levels should have plain surface. As light as possible. Material of the formwork should not warp or get distorted when exposed to the elements. Should rest on firm base. The following points are to be kept in view to effect economy in the cost of formwork. The plan of the building should imply minimum number of variations in the size of rooms, floor area, etc. so as to permit reuse of the formwork repeatedly. Design should be perfect to use slender sections only in a most economical way. Minimum sawing and cutting of wooden pieces should be made to enable reuse of the material a number of times. The quantity of surface finish depends on the quality of the shuttering. Material for formwork construction. Among the material that can be used for construction of shuttering: timber, steel, glass reinforced plastic. Among the advantages of timber shuttering are as follow: easy handling because it's lightweight, easy to disassemble, damaged parts can be replaced with new one, very flexible. Among the advantages of steel shuttering are as follow: can't be used for long. Have limited reuse, can only be reused 5 or 6 times. If the timber is dry, it will absorb moisture from wet concrete, which could weaken the resultant concrete member. Timber with high moisture content, more than 20% moisture content, wet concrete will shrink and cup, leading to open joints and leakage of grout. Plywood. This is by far the most common material used for the facing panel. It is easily cut to shape on site, and if handled and stored carefully, it can be used many times. A standard plywood thickness on site is 18 mm. This is usually sufficient for most powers. However, if the formwork is curved, a thinner plywood is used to facilitate bending. Thicker plywood may be used when the weight of concrete causes a standard thickness plywood to bow out, distorting the concrete face. Steel formworks. Steel forms are stronger, durable, and have longer life than timber formwork, and their reuses are more in number. Steel forms can be installed and dismantled with greater ease and speed. The quality of exposed concrete surface by using steel forms is good, and such surfaces need no further treatment. Steel formwork does not absorb moisture from concrete. Steel formwork does not shrink or warp. Aluminum formworks. Often used in prefabricated formwork, that is put together on site. Aluminum is strong and light, and consequently fewer supports and ties are required. The lighter sections will deflect more, but this can be avoided by simply following the manufacturer's recommendations. Plastic formworks. Glass reinforced plastics, GRP, and vacuum-formed plastics are used when complicated concrete shapes are required, e.g. waffle floors. Although vacuum-formed plastics will always need support, GRP can be fabricated with integral bearers, making it self-supporting. Like steel, plastic formwork can be reused many times, as long as care is taken not to scour the surface whilst vibrating the concrete. Formwork. Technical, functional, economical, and safety requirements. There are several requirements that formwork structure need to meet, otherwise it would not serve its purpose adequately. In order to make sure that the form structure fulfill its design goals, the designer and site engineer should take technical, functional, economical, and safety requirements of the forms into consideration. The fulfillment of these requirements would guarantee safe, strong, and robust formwork structure and provide safe working condition for laborers. Formwork is a temporary mold into which fresh concrete and reinforcement are placed to form a particular reinforced concrete element. It supports part or the whole of a permanent structure until it is self-supporting. Technical requirements of formwork. Formwork should be of the desired shape, size, and fit at the location of the member in structure according to the drawings. It should be carefully selected for required finish surface and linings to produce the desired concrete surface. Formwork need to withstand the pressure of fresh concrete and working loads and should not distort or deflect from their position during the concrete placement operation. The formwork must not damage the concrete edge or surface, or themselves during removal from structure. Panels of the formwork should be tightly connected to minimize gap at the formwork connection to prevent leakage of cement paste. Functional requirements of formwork. Formwork sections should be sized in a manner that can be lifted and transported easily from one job site to another. It should be dismantled and moved as easily as possible. Interchangeability of formwork units is another functional requirement. This enables units to be used for forming different members. Formwork shall be designed such that it fits and fastens together with reasonable ease. Simplicity in erection is another valuable functional requirement of forms. Formwork should be as lightweight as possible without any strength reduction. Economic requirements of formwork. Formwork shall be made of low-cost materials. Energy consumption and labor cost should be as minimum as possible. Repetitive utilization of formwork is another economic requirement that must not be compromised. So, they must be able to withstand a good number of reuses without losing their shape. Formwork structure must be designed so that the whole formwork system can be assembled and dismantled with unskilled or semi-skilled labor. Maintenance of formwork is required to be conducted based on applicable standards. How to set good safety plan for concrete formwork system. Good safety plans for formwork system ensure execution of construction project as per established construction practice and avoid undesired events such as failure of formwork and consequent delay in construction and possible loss of life. Commonly, safety shall begin in the planning and management of a project. Construction work supervision, equipment utilization practices, and construction procedure used must ensure the safety of workers and the public. Formwork designers, project planners, and managers need to follow the requirements of applicable standards such as OSHA regulation in order to produce good safety planning. Supervision and inspection. Practicing proper supervision during formwork placement, concrete pouring, and stripping of formworks is essential for obtaining safety in the use of forms. A supervisor's task is to ensure the erection of formwork according to the design and practicing a safe erection procedure to avoid overloading of members. Filed modification in the false work, forms, or erection procedure should be permitted unless the form designer is consulted. The exertion of unusual loads shall be prevented if the formwork system is not designed for such loads. Platforms and access for workers. Accessible working platform shall be prepared for works executed at elevated positions. Long ladder to the tops of false work needs to have rest or passing platform. In certain structures such as bridges, it might be necessary to use special scaffolds or any other suitable equipment for stripping decks and piers forms. Safety signs and barriers should be placed to keep the unauthorized individuals out of the working area during erection and striping formwork system. Platforms and access means for worker need to conform with applicable codes such as OSHA requirements. The provision of accessible and safe working area can be provided if engineers and experienced field personnel cooperate with each other. Control of concreting practices. Controlling concrete pouring is a major factor in the safety plan establishment. The sequence and rate of concrete placement should consider limitations provided in the formwork drawings. While concrete is placed, unbalanced form loading shall be prevented. For instance, in beam and slab construction, fill the beams first and then work outward equally on both sides when placing the slab. The stability of the formwork system can be enhanced in a column and slab structure by concreting the columns at least a day ahead of the slab. Hardened concrete in the columns offers additional lateral stiffness to the formwork structure during concreting of the slab. Frequently, reinforced concrete column is constructed and then erection of floor system begins. Hardened concrete in the columns offers additional lateral stiffness to the formwork structure during concreting of the slab. Frequently, reinforced concrete column is constructed and then erection of floor system begins. Improving soil bearing and bracing. Commonly, the condition of soil is not known when the forms and scaffoldings are designed, assumed bearing capacity is used. So, it would be the task of contractor to check whether the bearing capacity of the soil at construction site is greater or smaller than the one assumed during design stage. If soil bearing capacity is questionable, then it can be stabilized by tamping or covered with layer of crushed stone. Formworks shall be designed to prevent progressive collapse due to localized failures. Shoring and reshoring. Installation of out-of-plumb shores, bent jacks, and defective timber shall be avoided, otherwise these supporting elements would support only a small portion of design loads. During concreting, Forms shall be monitored continuously in order to observe problems and correct them as soon as they arise. Safety requirements of formwork. Formwork needs to be manufactured such that workers can handle them without any safety issue. Health, safety, and hygiene regulations should be considered while forms are made. Stability of the whole structure should be checked and ensured to avoid any undesired events which may cause loss of life, delay construction, and increase cost. Emergency escape route shall be provided. Emergency response plan need to be established. All reasonably practicable steps shall be taken to eliminate any foreseeable risk arising from the work to be done. If it is not possible to eliminate the expected risk totally, then control measures and safe work procedures shall be implemented to minimize and control the risk. Requirements of good formwork. It should be strong enough to withstand all types of dead and live loads. It should be rigidly constructed and efficiently propped and braced both horizontally and vertically, to retain its shape. The joints in the formwork should be tight against leakage of cement grout. Construction of formwork should permit removal of various parts in desired sequences without damage to the concrete. The material of the formwork should be cheap, readily available, and should be suitable for reuse. The formwork should be set accurately to the desired line, and levels should have a plane surface. It should be as light as possible. The material of the formwork should not warp or get distorted when exposed to the elements. It should rest on a firm base. Economy in formwork. The following points are to be kept in view to effect economy in the cost of formwork. The plan of the building should imply a minimum number of variations in the size of rooms, floor area, etc. to permit reuse of the formwork repeatedly. Design should be perfect to use slender sections only in the most economical way. Minimum sawing and cutting of wooden pieces should be made to enable reuse of the material many times. The quantity of surface finish depends on the quality of the formwork. Formwork can be made out of timber, plywood, steel, precast concrete, or fiberglass used separately or in combination. Steel forms are used in a situation where large numbers of reuse of the same forms are necessary. For small works, timber formwork proves useful. Fiberglass made of precast concrete and aluminum are used in cast in situ construction such as slabs or members involving curved surfaces. Types of formwork, shuttering. Timber formwork. Timber for formwork should satisfy the following requirement. It should be well seasoned, light in weight, easily workable with nails without splitting. Free from loose knots. Timber used for shuttering for exposed concrete work should have smooth and even surface on all faces which come in contact with concrete. Normal sizes of members for timber formwork. Sheeting for slabs, beam, column side, and beam bottom. 25 mm to 40 mm thick joints, ledges. 50 x 70 mm to 50 x 150 mm posts. 75 x 100 mm to 100 x 100 mm. Plywood formwork. Resin bonded plywood sheets are attached to timber frames to make up panels of the required sizes. The cost of plywood formwork compares favorably with that of timber shuttering, and it may even prove cheaper in some instances given the following considerations. It is possible to have a smooth finish, in which case on cost in surface finishing is there. By the use of large size panels, it is possible to effect saving in the labor cost of fixing and dismantling. The number of reuses are more as compared with timber shuttering. For estimation purposes, the number of reuses can be taken as 20 to 25. Steel formwork. This consists of panels fabricated out of thin steel plates stiffened along the edges by small steel angles. The panel units can be held together through the use of suitable clamps or bolts and nuts. The panels can be fabricated in large numbers in any desired modular shape or size. Steel forms are largely used in large projects or in a situation where large number reuses of the shuttering is possible. This type of shutter is considered most suitable for circular or curved structures. Comparison between steel and timber formwork. Steel forms are stronger, durable, and have a longer life than timber formwork, and their reuses are more in number. Steel forms can be installed and dismantled with greater ease and speed. The quality of exposed concrete surface by using steel forms is good, and such surfaces need no further treatment. Steel formwork does not absorb moisture from concrete. Steel formwork does not shrink or warp. Types of formwork, shuttering, based on structural member. Formworks are used in construction of reinforced concrete foundations, columns, slabs, walls, etc., and these are named as follows. Footing forms. Formworks for foundation. Column forms. Formwork for RCC column construction. Wall forms. Formwork for RCC wall construction. Floor forms. Formwork for construction of RCC slabs. Footing forms. Formworks for foundation. The first step for any concrete construction starts with the construction of foundation. Foundation can be for columns or walls. So, based on type of structural member, the shape and size of footing are designed. Thus formwork size and shape depends on the type and dimension of the footing. Components of footing forms. Figure showing components of footing formwork, for shallow footing, continuous footing formwork. Column forms formwork for concrete column construction. Reinforced concrete column forms are subjected to lateral pressure because of their small cross-section, large heights, and relatively high rates of concrete placement. Thus it is necessary to provide tight joints and strong tie support to the formwork. As the sizes of concrete column increases, the stiffness of the formwork must be increased by either increasing thickness of sheathing or vertical stiffeners must be added to prevent sheathing deflection. Wall forms formwork for RCC wall construction. Formwork for wall construction are subjected to relatively lower lateral pressure than column forms due to their large cross-sectional area. The components of wall forms are: panel sheathing. It is used to shape the wall and retain the concrete until it sets. Studs to support the sheathing or wales by forming a framework to keep the forms aligned and support the studs. Braces. It is used to prevent deflection of forms under lateral pressure and keep the formwork erect. Ties and spreaders. These are used to hold the sides of the forms at the correct spacing. Floor forms formwork for construction of RCC slabs. Formwork for reinforced concrete slabs depends on the type of slabs to be constructed. The floor slabs can be structural slabs supported on a steel or concrete structural frame, or slab on grade. The design of formwork varies with the type of slab. Structural slab formwork assembly is carried out as follows. Positioning of the girder or beam form at the bottom. Girder side forms overlaps the bottom form and rests on the shore heads and the sides of the column form. Side forms is held in place by ledger strips nailed to the shore heads with double-headed nails. Larger girders should have the side forms vertically stiffened to prevent buckling. When constructing the girder and beam forms, each part must be removed without disturbing the remainder of the form. Strike-off formwork will commence with the beam and girder sides, followed later by the column forms, and finally by the beam and gird bottoms. Slab on grade forms are forms for concrete slabs placed on grade. These slab formworks are usually quite simple as concrete is placed on compacted earth or gravel leveled base. Thus no support is required for concrete at the bottom. Slab on grade formwork assembly is carried out as follows. Plank, plywood, or steel forms are used for forming supporting the open edges of concrete. These forms are held in place by supporting with wooden pegs. The reinforcement in slab, if specified in the structural drawing, should be placed on its proper location according to the drawing on chairs, bolsters, and spacers made of either metal or concrete. If the slab is to be cast in sections, construction joints must be provided between them, which will transmit shear from one to the other. Different materials used for formwork advantages and disadvantages. A formwork is a temporary structure used as mold for the original structure. There are different materials available to construct the formwork. Formwork material is selected depending upon many factors like cost, requirement, type of structure, etc. Different formwork materials. Different formwork materials and their advantages and disadvantages are discussed below. Timber, plywood, steel, aluminum, plastics, magnesium, fabric. Timber as formwork material. Timber is the most commonly used material for formwork. Timber logs, lumber, etc. are used as bracing members from ancient times. So, the timber formwork is also called as traditional formwork. It is most economical material used for formwork. This is used in sites as formwork material for number of years, so the method of constructing timber framework is well known to the workers. Advantages. Timber can be cut into any required size easily. Timber is light in weight and it can be handled easily. Timber has good thermal resistance, which prevents the damage of concrete in colder regions. It is easy to understand the construction method of timber formwork, hence, skilled workers are not necessary. It is easy to replace the damaged parts of timber forms. Timber formwork can be easily dismantled. Disadvantages. Dry timber may absorb water from wet concrete, which result in the reduction of strength in concrete structure. Wet timber having high moisture content compress the wet concrete and forms cracks in the structure, and grout may leak through joints when shrinking occurs. Timber forms have limited usage, so they cannot be useful for more times. Plywood as formwork material. Plywood, which is a manufactured product of timber, is also used for formworks. It consists number of veneer sheets or plies in layers. Nowadays, the use of plywood formwork increases, especially for facing panels. The reason behind it is that the plywood formwork provides smooth finish when compared to normal timber formwork. Hence, finishing cost may reduce by the use of plywood. For formwork, special type of plywood called exterior plywood is used. The veneer sheets of exterior plywood are bonded with strong adhesive to make it watertight. The plywood boards are available in thicknesses from 7 mm to 32 mm. In general, plywood of size 1220 x 2440 and 18 mm thick boards are sufficient for most of the works. For curved structures, Special types of plywood with sufficient thickness are also available. Advantages: plywood can also be cut into required size easily. Plywood strong, durable, and light in weight. Provides smooth finish on the surface. Very large size plywood sheets are available, which makes the construction of formwork quicker and easier. Curved formworks can also be prepared using plywood. When compared to timber, it gives more number of reuses. Disadvantages: when compared to timber, it is costly. Thin plywood sheets cannot sustain the weight of concrete. They may bow out if proper thickness is not provided. Steel as formwork material. Steel can also be used as formwork material. It is very costly, but it can be used for more number of times than others. They provides excellent finish to the concrete surfaces. For mass structures like dams, bridges, etc., steel from work is so strong and safe. Advantages: steel forms are durable and stronger. Provides uniform and smooth surface finish to the structure. Great reusability. Easy to fix the formwork and also easy to dismantle. Disadvantages: cost is very much higher. It is heavy in weight and requires lifting equipment for large structure formworks. Corrosion will occur when there is a frequent contact with water. The size and shapes of forms available are limited. Aluminum as formwork material. Aluminum formwork is used often for prefabricated formworks. It is getting more popular because of its lightweight and good strength. It requires fewer supports and ties. Advantages: easy to fix and easy to dismantle. It can be handled easily because of its light weight. It can be reused for many times. The walls and slabs of structures can be cast simultaneously. Monolithic crack-free structures can be built using aluminum formwork. Disadvantages: when the load reaches its maximum limit, the lighter sections may deflect. Architectural modifications are not possible when aluminum formwork is used. Plastics as formwork material. Plastic is another type of formwork material which is used for small concrete structures or for complex portions of the structure. It is light in weight and durable for long periods. For complicated concrete structures, glass reinforced plastics, GRP, and vacuum-formed plastics are used. Advantages: plastic is light in weight and can be easily handled. Formwork for complex-shaped structures can be prepared easily. Good resistant against water. The damaged plastic sheets can be recycled and useful to make new sheets. Good quality plastic has great reusability. Disadvantages. Plastic is weak against heat. It is costly material. It does not take much load when compared with others. Magnesium as formwork material. Magnesium is another metal element which is used for formwork. Magnesium is not directly used for formwork and is used with the combination of oxygen atoms which forms magnesium oxide, usually called magnesia or MgO. Magnesium oxide boards or MgO boards are famous in some countries because of their multiple applications. MgO boards are available in required sizes and grades. Advantages. MgO boards are light in weight and easy to handle. They are fireproof and waterproof. Bio-friendly boards cause no harm to the environment. They are strong to resist heavy loads. Disadvantages. When MgO boards meet wet concrete, the magnesium chloride present in MgO boards may dissolve and cause corrosion to the reinforcement. Skilled supervision is required for installation. MgO boards cannot sustain in humid conditions. They absorb moisture easily from atmosphere, so they are called as crying boards. Fabric as formwork material. Fabric formwork is the modern technology in construction sector. Fabric can be molded into any required shapes, which makes it more famous formwork for architectural purposes. Advantages. It weighs very less when compared to any other formwork material. It is economical. Any complex shape can be constructed using fabric formwork. It is waterproof. Doesn't affect the concrete properties. Easy to removal after the hardening of concrete. Disadvantages. For installation, skilled workers are required to form perfect and required complex shapes. Concrete formwork design considerations. Basis for concrete formwork design. Design and building concrete formwork effectively requires a basic understanding of how concrete behaves as it exerts pressure on formwork. Concrete exerts lateral pressure on the formwork. The formwork is designed based on these lateral forces. Concrete formwork design considerations. Lateral concrete pressure on formwork is affected by height of concrete pour, concrete pour rate, weight of concrete, temperature, type of cement, vibration, concrete slump, water, cement ratio, chemical additives. Height of concrete pour. Before concrete hardens, it acts like a liquid and pushes against the forms the way water presses against the walls of a storage tank. The amount of pressure at any point on the form is directly determined by the height and weight of concrete above it. Pressure is not affected by the thickness of the wall. Concrete pour rate. Concrete pressure at any point on the form is directly proportional to the height of liquid concrete above it. If concrete begins to harden before the pour is complete, the full liquid head will not develop and the pressure against the forms will be less than if the pour were completed before any of concrete hardened. Once concrete hardens, it cannot exert more pressure on the forms even though liquid concrete continues to be placed above it. The following diagrams illustrates how form pressure varies when the pour rate is increased from one level to another level. For ease of explanation, it is assumed that concrete hardens in 1 hour, typically, at 21 degrees Celsius. Weight of concrete. Pressure exerted against the forms is directly proportional to the unit weight of concrete. Lightweight concrete will exert less pressure than normal weight concrete as shown below. Temperature. The time it takes concrete to harden is influenced greatly by its temperature. The higher the temperature of the concrete, the quicker it will harden. Most formwork designs are based on an assumed average air and concrete temperature of 21 degrees Celsius. At low air temperatures, the hardening of concrete is delayed and you need to decrease your pour rate or heat your concrete to keep the pressure against the formwork from increasing. Ideally, concrete should be poured at temperatures between 16 degrees and 38 degrees Celsius. Outside this temperature range there is often insufficient moisture available for curing. If adequate water for curing is not available or freezes, the strength of the concrete will suffer. Chemical additives. When using chemical additives, i.e. retarders, plasticizers, etc., make sure to refer to the vendor's application data. Type of cement. The cement type will influence the rate at which concrete hardens. A high early strength concrete will harden faster than normal concrete and will allow a faster pour rate. When using cement which alters the normal set and hardening time, be sure to adjust the pour rate accordingly. Vibration. Internal vibration consolidates concrete and causes it to behave like the pure liquid. If concrete is not vibrated, it will exert less pressure on the forms. ACI recommended formulas for form pressures may be reduced 10% if the concrete is spaded rather than internally vibrated. Revibration and external vibration result in higher form loads than internal vibration. These types of vibration require specially designed forms. Concrete slump. When concrete has very low slump, it acts less like a liquid and will transmit less pressure. When using concrete with a slump greater than 100 mm, the formwork should be designed to resist full liquid head. Construction of concrete formwork. This normally involves the following operations: propping and centering, Shuttering. Provision of camber. Cleaning and surface treatment. Order and method of formwork removal. The sequence of orders and method of removal of formwork are as follows. Shuttering. Forming the vertical faces of walls, beams, and column sides should be removed first as they bear no load but only retain the concrete. Shuttering. Forming soffit of slabs should be removed next. Shuttering. Forming soffit of beams, girders, or other heavily loaded shuttering should be removed in the end. Rapid hardening. Cement, warm weather, and light loading conditions allow early removal of formwork. The formwork should under no circumstances be allowed to be removed until all the concrete reaches a strength of at least twice the stresses to which the concrete may be subjected at the time of removal of formwork. All formworks should be eased gradually and carefully in order to prevent the load from being suddenly transferred to concrete. Period of removal of formwork. No. Description of structural member. Time period 1. Walls, columns, and vertical sides of beams. 1 to 2 days. 2. Slabs, props left under. 3 days. 3. Beam soffits, props left under. 7 days. 4. Removal of props to slabs. A. 4 slabs spanning up to 4.5 m. 7 days. B. 4 slabs spanning over 4.5 m. 14 days. 5. Removal of props to beams and arches. B. Spanning over 6 m. 21 days. A. Spanning up to 6 m. 14 days. Factors affecting concrete formwork striking times. The striking time of concrete formwork depends on the strength of structural member. The strength development of concrete member depends on grade of concrete. Higher the grade of concrete, the rate of development of strength is higher and thus concrete achieves the strength in shorter time. Grade of cement. Higher cement grade makes the concrete achieve higher strength in shorter time. Type of cement. Type of cement affects the strength development of concrete. For example, rapid hardening cement have higher strength gain in shorter period than the ordinary Portland cement. Low heat cement takes more time to gain sufficient strength than OPC. Temperature. The higher temperature of concrete during placement makes it achieve higher strength in shorter times. During winter, the concrete strength gain time gets prolonged. A higher ambient temperature makes the concrete gain strength faster. Formwork helps the concrete to insulate it from surrounding, so longer the formwork remain with concrete, the less is the loss of heat of hydration and rate of strength gain is high. Size of the concrete member also affects the gain of concrete strength. Larger concrete section members gain strength in shorter time than smaller sections. Accelerated curing is also a method to increase the strength gain rate with the application of heat. Strength of concrete versus structural member type and span for formwork removal. Concrete strength. Structural member type and span 2.5 N/mm2. Lateral parts of the formwork for all structural members can be removed. 70% of design strength interior parts of formwork of slabs and beams with a span of up to 6 m can be removed. 85% of design strength interior parts of formwork of slabs and beams with a span of more than 6 m can be removed. Formwork stripping time, when ordinary Portland cement is used. Type of formwork. Formwork removal time. Sides of walls, columns, and vertical faces of beam 24 hours to 48 hours, as per engineer's decision. Slabs, props left under. 3 days beam soffits, props left under. 7 days removal of props of slabs. I. Slabs spanning up to 4.5 m. 14 days 2. Slabs spanning over 4.5 m. 14 days removal of props for beams and arches I. Span up to 6 m. 14 days 2, span over 6 m. 21 days. What is insulating concrete formwork? How it is used in construction? What is insulating concrete formwork? Insulating concrete formwork, ICF, is a building system that uses lightweight formwork made from an insulating material to support concrete walls whilst they are being cast in situ, and which is then left in place as insulation. Used on the continent and in North America for many years, ICF has proved to be robust, cost-effective method of constructing a variety of building types, from houses and basements to multi-story cinemas and commercial buildings. How is insulating concrete formwork used? Insulated concrete formwork consists of twin-walled expanded polystyrene panels that are stacked together to create the permanent formwork used to contain the ready mixed concrete for the walls. The insulated formwork remains in place to provide complete thermal insulation to the walls of the finished building. It also provides a uniform surface ready for direct application of most finishes and proprietary cladding systems. Many insulated concrete formwork systems also incorporate their own flooring system. Design considerations of insulating concrete formwork. The blocks that make up the insulating formwork are manufactured in a variety of shapes and component types, creating limitless design opportunities. For example, Features such as bay windows and arches can be generated without having to resort to specialist products. In addition, floors can be constructed using ICF components. Any type of foundation, flooring, partition, stair, or roofing system is compatible with ICF construction. ICF provides an easy means of achieving high standards of structural, energy, fire and acoustic performance. The exterior of the building can be clad in any finish the architect requires, including masonry, brick slips, render tiles, curtain walling and weatherboarding. Internally, plaster or dry lining is applied directly to the face of the expanded polystyrene formwork. Advantages of insulating concrete formwork for the builder. Insulating concrete formwork is quick and easy to use without the need of skilled tradesmen. In fact, any builder can quickly erect an ICF structure since the lightweight units are easier to handle than traditional materials. Typically, an experienced team of 4 can erect and concrete the walls of a 3-bedroomed bungalow in a day, significantly reducing the contract program. The low labor and reduced need for skilled tradesmen result in more efficient use of increasingly scarce construction workers. Also, with the speedy construction of watertight building envelope, internal services and finishings can progress independently of external cladding. Service ducts and utilities can be pre-installed within the concrete core or chased into the expanded polystyrene using a router of hot wire cutter. ICF components and temporary bracing systems are delivered as lightweight portable packs, which do not require mechanical handling or the use of special tools. Just-in-time deliveries and direct placement of ready mixed concrete reduces waste and site storage facilities. Also, the energy-efficient building allows downsizing of the boiler. Concrete formwork checklist during concreting and striking. Concrete formwork checklist includes checks to be carried out before concreting, during concreting and after removal of formwork. Concrete formwork possesses both quality and safety threats. If the formwork is not right for the concrete and work is being done at height, it may cause safety issue. Concrete formwork is a temporary supporting structure for concrete when it is placed at the construction site to keep the concrete in position and shape till it gets hardened. Quality of concrete is affected when the formwork is not properly aligned, not leak-proof, etc. Proper storage of concrete formworks is also required for cost economy of the project. Concrete formwork checklist at site. Formwork checklist for walls. Ensure lateral bracings provided firmly supports the forms at all points of support. Block out, stop end, brace to resist vertical and lateral loads. Form panels are adequately braced and tied with each other. Formwork corners shall be adequately tied to prevent leakage or bulging and spreading of concrete. Ensure sufficient length is provided for wall ties and has sufficient strength and spacing as required. Check wales for proper spacing, and joints between should be staggered from one tier to the next. In double member wales, one member left continuous across the location of form ties. Wall ties and bolts tightened properly. In case double member wales is used, both wales should have identical depths. Check for adequate lap between forms and previously cast concrete. Ensure that grout leakage does not occur at joints between panels and joints between old concrete and panels above them. Check the provision of resistance against uplift in case of sloping faces of concrete formwork. Ensure experienced supervisor is available at site while installing the wall forms and while placing concrete. Formwork checklist during concreting. Before concreting commences, ensure proper access for workers involved in placing, compacting and finishing concrete. Presence of experienced supervisor keeping a continuous watch for any dangerous situation. Adequate supply of spare props, clamps, bolts, wedges and skilled workers at site. Alignment, camber, level and plumb, verticality, maintained while concreting is in progress. Effective depth between top and bottom reinforcement not disturbed. Cover of concrete around reinforcement steel maintained as specified. Grout loss due to movement at joints and corrective action taken against it. Loosening of wedges and fixings due to vibrations transmitted to the formwork and corrective action against it. Spilt concrete and or grout cleaned immediately. All wooden spreaders, to hold vertical form faces apart, removed after placing concrete. Wooden members for creating pockets eased before concrete sets fully. Concrete pouring sequence as per that shown on formwork drawing. Avoid eccentric loading. Prevention of heaping of concrete and high impact drops from concrete buckets. Rate of concreting within allowable limits as shown on working drawing or as assumed while designing the formwork against lateral pressures. Proper bond between layers of concrete, in case concrete is placed in layers, by ensuring that needle vibrator while vibrating the top layer also penetrates the lower layer. Checklist during formwork striking, stripping or removal. Formwork design and layout such that smooth striking of formwork in sequential manner is possible. Strength of concrete capable of taking self-weight and construction load on it. Removal time to be ascertained depending on size, shape, and span of the member, grade of concrete mix and its rate of gain of strength, type of cement, ambient temperature, and weather conditions and extent of curing executed. At the time of removal of side form, corners, and edges not damaged. Ties, clamps and wedges loosened and removed gradually. Removal time in line with those specified in Code of Practice, IS 456-2000. Props in case of beams and slabs removed in stages from mid-span working outwards. Bolts, nuts, clamps, wedges collected in a box and not dropped carelessly. Use of crowbars to prise open forms avoided. Formwork prized loose using wooden wedges. Formwork carefully lowered and not dropped and damaged. Panel faces should be carefully removed and lowered without them hitting the scaffold projections. Panels placed on leveled surface after removal. Nail projections hammered down. Cordoning off the area below the location where formwork removal is proposed. Presence of competent crane operator and foreman. Checklist for cleaning and storage of formwork. Formwork as soon as it is removed, cleaned with a stiff brush. Dust, dirt, stubborn bits of concrete or grout removed. Timber surface and uncoated ply coated with release agent before storing. Steel form coated lightly with oil to prevent corrosion. Damaged formwork sorted out and repaired before storage. Depressions, nail holes repaired with suitable materials and lightly rubbed down to give smooth surface. Panels and plywood sheets stored on a horizontally leveled floor. Panels stored face to protect the surface. Storage area protected from rain and moisture and well ventilated. All formwork materials stacked off the ground. Loose wailing, soldiers, struts, etc. stored with respective panels after numbering for proper match when reused. Bolts, nuts, champs, pins, wedges, keys and ties stored in separate bins or boxes. Common defects in concrete formwork systems. Concrete formwork systems suffer from several deficiencies such as defects due to imperfect design and construction practice, defects in foundation level of formwork systems, defects in vertical support of formwork systems and defects in horizontal support of formwork systems. These common defects are discussed below. Formwork defects due to imperfect design and construction practice. Defects in foundation level of formwork systems. Defects in vertical support of formwork systems. Defects in horizontal support of formwork systems. Common defects in concrete formwork systems. Formwork defects due to imperfect design and construction practice. Too much tolerances in construction. Inability to control vertical rate of concrete placement. Inability to check the tightness of bolts and wedges before loading formwork systems. Insufficient allowance for uplift of concrete under inclined formwork systems. Different load distribution between two or more member that's supposed to support common loads. Incorrect computation of stresses because of oversimplification of design assumptions. Lack of required provision for the vibration effect on ties, struts, braces, and wedges. Failure to properly account for wind loads. Insufficient allowance for the influence of stresses generated by temperature, press stressing, and moisture movements. Defects in foundation level of formwork systems. Sole plates are not leveled. Crushing of sole plate because of insufficient distribution of loads form horizontal and vertical members. Poor load carrying capacity of the ground under sole plate. Deterioration of load carrying capacity of the ground, for instance washing out ground. Deterioration of sole plates with time because of several factors, for example weather condition. Defects in vertical support of formwork systems. Lack of ties between standards at point of loading. Supports are out of plumb. Insufficient bracing to scaffold. Bearing plates at the top and bottom of props are distorted. Insufficient lateral ties, vertical, and plan bracing. Lack of rigidity of screw connection because of lack of bracing or overextension. Utilizing adjustable steel props with nails, mild steel bolts and reinforcing bars instead of correct pins. Defects in horizontal support of formwork systems. Horizontal members are not centrally placed in fork heads. Lack of staggering in timber bolted connection, which may lead to split out of the timber bolted connection. Insufficient lateral and tensional bracing. Inadequate support to prevent overturning of deep principal elements, since fork heads are frequently omitted. Insufficient support to cantilevers. Inadequate bearing area to vertical supports and underside of main members lead to crushing. Folding wedges cut to too coarse a taper, not properly cleated, cut from wet material. What are the causes of concrete formwork failures? There are several factors that may lead to the failure of formwork during and after concrete placement. Improper bracing can cause formwork failure, since the weight of fresh concrete is no longer supported by formwork system. Unanticipated incident can make member to fail, and subsequent overloading or misalignment of other members results in the failure of the entire formwork structure. Moreover, omissions in the assembly detail is another factor that cause concrete formwork failure. This is because localized weakness and overstress would occur, which destabilize the formwork system. Furthermore, workmanship errors due to haste, indifference, or lack of knowledge is another cause of failure. Finally, formwork failures can lead to loss of life, delay in construction, and increase construction cost. That is why familiarizing with causes of failure and considering proper prevention strategies are substantially crucial. Good practice in designing, constructing, and handling formwork can provide safety as well as efficiency and economy. Improper stripping and shore removal. Early striping of forms and careless practices in reshoring can lead to failure of formworks and total failure of specifically in multistory building in which progressive collapse is highly likely. Sometimes, premature striping causes sagging of partially cured concrete. This leads to crack development and create maintenance issues. Insufficient spacing and size of reshores may lead to a formwork collapse during construction as well as damage of the concrete structure. Inadequate bracing. Insufficient cross-bracing and horizontal bracing of shores are common causes of formwork failure. This is because poor bracing generates lateral force and hence create lateral deformation of supporting members. When a failure occurs at one point, inadequate bracing may permit the collapse to extend to a large portion of the structure and multiply the damage. Inadequate control of concrete placement. Failure to regulate properly the rate and order of placing concrete on horizontal formwork introduce unbalanced loadings and consequent failures of formwork. So, concrete temperature, concrete chemistry, rate of vertical placement of concrete, and vibration of concrete are factors affecting the development of lateral pressures that act on the forms. If concrete temperature drops during construction operations, the rate of concrete placement needs to be decreased to avoid a buildup of lateral pressure overloading the formworks. Inadequate concrete strength development. It is another factor that has been reported to be the cause of concrete formwork system. The failure of hyperbolic cooling tower, which is located in Ohio/USA, during its construction is compelling example of failures due to insufficient concrete strength development. A jump form system was supported by anchors cast in the previous day's concrete placement. The forms were linked together around the inside and outside of the circular shell structure. After raising the forms and during the casting of an additional ring level, the concrete placed the previous day failed at the anchors, causing the scaffolding and forms to collapse. Vibration and impact. Vibration and impact due to passing traffic, movement of workers and equipment on formwork, and vibration because of concrete consolidation can displace supporting shores or jacks of formwork system and cause total failure of the forms. Unstable soil under mudsills and out of plumb shores. Unstable soil and out of plumb shores are another factor that jeopardize the stability of the formwork system. Unstable soil would lead to differential settlement and the ability of out of plumb shores to support loads declined greatly. Therefore, verticality of shores and the sufficient ability of soil to support loads shall be ensured during the construction of formwork system. Supporting elements of formwork should not be placed on frozen ground. This is because moisture and heat from the concreting operations or changing air temperatures may thaw the soil and allow settlement that overloads or shifts the formwork. Finally, site drainage must be adequate to prevent a washout of soil supporting the mudsills. Lack of attention to formwork details. Assemblage errors such as insufficient nailing, failure to tighten the locking devices on metal shores, inadequate provisions to prevent rotation of beam forms where slab forms frame into them on one side, inadequate anchorage against uplift for sloping form faces, and lack of bracing or tying at corners can cause failure of formworks even if its design is completed in the best possible way. So, skilled and trained labor shall assemble the formwork system under great supervision. When formwork is not at fault. There are cases in which the failure of the formwork system during building construction is not related to formwork faults. Factors such as incorrect assumption regarding types of soil in design stage, inadequate shear reinforcement placement, and placement of ducts at high stress region in slabs are reported to be the causes of failures.
Thank you for watching. For now, please subscribe, like, share and do not forget to press bell icon.